So today we're going to be discussing what are known as vector lengths, the length of vectors actually, vector lengths. And we'll be actually applying it and considering what it means in the context of bras and cats, which are essentially, vectors that are either a single row or a single column. Now, when we talk about vector length, let's consider a certain example, a very simple one. So if you're given a test, and before you even look at the questions, and you consider to yourself, what is the easiest possible question I can get about vector lengths. I'm so hopeful if I forgot to study. What is the easiest question I would want to get? And in this case, that would just be a vector with, say, two elements, right? Let's say it's 1, 2. And actually, if we rewrite it as 1, 2, this actually starts looking a bit like a coordinate point. And so let's put it that way. Let's illustrate this on a graph of some sort and say this particular vector begins at the origin. This is your x, this is your y. So it's goes over by 1, up by 2. And so your start point once again is at the origin. Your end point is over here at 1, 2, right? And this is what your vector looks like. Alright, so now that we have drawn our vector, and again, you can have a vector that can be translated anywhere along this graph that we have here, this Cartesian coordinate plane that we have here. But if we look at this vector, one of the things that might pop up to you is the consideration that if we actually connect all these dots and all these parts, right, this is 2, this is 1, that we have here, we end up with something that resembles a right triangle. And if you go back to your maybe days in geometry class, you might recall something known as the Pythagorean Theorem. Pythagorean Theorem. Right? And essentially, that basically says that if you have given side lengths A, B, and C, where this is a right triangle and A and B are your leg lengths, then C squared, right, which is the length of your hypotenuse, the longest leg, not the longest leg, the longest side of your triangle is equal to A squared plus B squared. Alternatively, we can just write it as C is equal to the principal root, the positive root of A squared plus B squared. And so this is where things get interesting. Once again, we have applied only a 2-element vector here. But actually, if we take any vector, any one row or one column vector that we have, and let's write it in this way: A1, A2, A3, all the way up to AN. Actually, the length of this given vector that we have here is equal to the square root, right? Going back to the Pythagorean theorem that we established earlier, square root of each of its elements squared, the sum of each of its elements squared. So A1 squared plus A2 squared plus A3 squared all the way up until AN squared. And that's essentially the length of a vector. It's a very simple, quite straightforward concept. Now, as a quick review and as a quick reminder, let's consider what this means in terms of bras and cats. And as and just in case you may not be familiar with these concepts, a bra vector can be written in such a way such that this is the general notation is equal to something like this, the given number of elements, n elements. On the other hand, a cat vector is written in this notation, and we rename that as B, right? Is written in this notation. By the way, A and B here just represent the names of these vectors, and A1, A2 are just elements within these particular matrices or vectors that we have. Is written, instead of being a single row, it is written as a column. So say B1, B2, so on and so forth until we get to its nth element, Bn. And so what's nice about vector lengths, in a sense, is that if we consider bras and cats, they can actually be written quite neatly, and you can find a relationship between the multiplication, actually, of bras and cats. And later on, it will come to define a very interesting property relating to these subjects. And so let's start from the very beginning. So let me shrink this particular, visual definition that we have right here. And very briefly, let's consider the following. So if you want to find the length, and this is how you denote a length, it's similar to like an absolute value kind of function that looks a little bit like that. But if you want to find the length of some bra vector A, this can fundamentally be written as the square root of a1 squared plus a2 squared, just what we established earlier on, an squared, right? Now let's consider a bra and a ket vector, and let's say they have an identical list of elements, and it's quite simple basically. So in this case, A would be like this, right? And if you have a ket vector, also named A, with the same elements, it would just be, A1, A2, so on and so forth until you get to AN, where the first element in your ket vector of A is identical to your first element in your bra vector A. And so let's consider what happens if we take our bra and our ket vectors and we multiply them together. So if we multiply them together, and actually if you want to write this in shorthand, we can squish them together, right, up until the point that they look like this. And this is just basically saying we're multiplying these two vectors that we have here, this bra and this ket vector. It's quite a neat little cute little way of writing it. And so if we take that and if we consider what this multiplication here writes out to be, and to become, if you remember from the multiplication video, this is essentially taking this, right, and let me add in this just for a visual representation. This is your ket vector, and then your bra vector, A1, A2, AN, right? We're just taking our first elements and we're multiplying them by each other. So it's A1 times A1, right? And then A2 times A2 plus A2 times A2 plus A3 times A3, right? All the way up until we reach AN times AN. And actually, if you look a little bit closer, keep in mind that these are the same elements. We defined earlier that this bra and this ket vector both have the same elements, just written in a slightly different way. We can just write this as A1 squared plus A2 squared plus so on and so forth until you get to AN squared. And so what's curious and what's quite interesting is if we look a little bit closer, actually, if we add a little bit of a square root on top of this multiplication between your bra and your ket vectors, these two statements become almost equivalent in a sense, and thus can be said that the length of a given bra or of a given ket vector, right, is equal to the square root of essentially this multiplication statement right here. And so this actually will later on tie into what is known as orthogonality in regards to these vectors, and we'll be defining that in a slightly later video. Alright, so just to very briefly recap, we went over what is known as vector, the length of vectors, where you use something similar to the Pythagorean Theorem, and you take the squares of every element within your given bra or your ket vector, and you add them together, and you take the square root of that in order to come up with the length. And in this case, if you take a bra vector, if you take a ket vector and you multiply it by one that is of the opposite sort, if you have a ket vector, you multiply it by a bra vector with the same exact elements, and vice versa, in these positions, in these corresponding positions, then actually you get this very curious, very interesting relationship, such that the length, and this is the notation for length of your given vector, is equal to the square root of the multiplication of this vector multiplication statement that we have right here. Alright, that's it for today. Stay curious, keep learning. Again, if you have any questions, don't hesitate. Please do not hesitate to visit the qmunitytech website. Thank you.